In physics, angular momentum is the rotational analog of linear momentum. It is an important quantity in physics because it is a conserved quantity. The angular momentum of a system remains constant unless acted on by an external torque. Angular momentum is related to the rotation or revolution of matter. The conservation of angular momentum explains many observed phenomena. For example, the increase in rotational speed of a spinning figure skater as the skater's arms are contracted, the high rotational rates of neutron stars, the falling cat problem and precession can all be explained in terms of angular momentum conservation. It has numerous applications in physics, engineering and everyday life. For instance, the gyro compass, control moment gyroscope, inertial guidance systems, reaction wheels, tops, flying discs or frisbees and Earth's rotation. Angular momentum in classical mechanics. Definition: scalar, angular momentum in 2 dimensions. Angular momentum is a vector quantity that represents the product of a body's rotational inertia and rotational velocity about a particular axis. In the simple case of revolution of a particle in a circle about a center of rotation, the particle remaining always in the same plane and having always the same distance from the center, it is sufficient to discard the vector nature of angular momentum, and treat it as a scalar. Angular momentum can be considered a rotational analog of linear momentum. Thus, where linear momentum is proportional to mass and linear speed, angular momentum is proportional to moment of inertia and angular speed. Unlike mass, which depends only on amount of matter, moment of inertia is also dependent on the position of the axis of rotation and the shape of the matter. Unlike linear speed, which occurs in a straight line, angular speed occurs about a center of rotation. Because for a single particle, and for circular motion, angular momentum can be expanded, and reduced to the product of the radius of rotation and the linear momentum of the particle, where in this case is the equivalent linear speed at the radius times to which the term moment of momentum refers. Vector, angular momentum in 3 dimensions. To completely define angular momentum in 3 dimensions, it is required to know the angle swept out in unit time, the direction of the axis of rotation, and the sense of the rotation, as well as the mass involved. By retaining this vector nature of angular momentum, the general nature of the equations is also retained, and can describe any sort of 3-dimensional motion about the center of rotation, circular, linear, or otherwise. In vector notation, the angular momentum of a particle in motion about the origin of coordinates is defined as, whereas the moment of inertia for a point mass is the angular velocity of the particle about the origin, is the position vector of the particle relative to the origin, is the linear velocity of the particle relative to the origin, and is the mass of the particle. This can be expanded, reduced, and by the rules of vector algebra rearranged to the form, which is the cross product of the position vector and the linear momentum of the particle. By the definition of the cross product, the vector is perpendicular to both and it is directed along the axis of rotation as indicated by the right-hand rule, so that the rotation is seen as counterclockwise from the head if the vector. Conversely, the vector defines the plane in which and lie. By defining a unit vector in the direction of the axis of rotation, a scalar angular speed results. Where is the perpendicular component of the motion, as above. The 2-dimensional scalar equations of the previous section can thus be given direction, and for circular motion, where all of the motion is perpendicular to the radius. Discussion: angular momentum can be described as the rotational analog of linear momentum. Like linear momentum, it involves elements of mass and displacement. Unlike linear momentum, it also involves elements of position and shape. Many problems in physics involve matter in motion about some certain point in space, be it in actual rotation about it, or simply moving past it. Where it is desired to know what effect the moving matter has on the point, can it exert energy upon it or perform work about it. Energy, the ability to do work, can be stored in matter by setting it in motion, a combination of its inertia and its displacement. Inertia is measured by its mass, and displacement by its velocity. Their product is the matter's momentum. Referring this momentum to a central point introduces a complication. The momentum is not applied to the point directly. For instance, a particle of matter at the outer edge of a wheel is, in effect, at the end of a lever of the same length as the wheel's radius. Its momentum turning the lever about the center point. This imaginary lever is known as the momentum. It has the effect of multiplying the momentum's effort in proportion to its length, an effect known as a moment. Hence, the particle's momentum referred to a particular point is the angular momentum, sometimes called, as here, the moment of momentum of the particle versus that particular center point. The equation combines a moment with a linear speed. Linear speed referred to the central point is simply the product of the distance and the angular speed versus the point. Another moment. Hence, angular momentum contains a double moment. Simplifying slightly, the quantity is the particle's moment of inertia, sometimes called the second moment of mass. It is a measure of rotational inertia. Because rotational inertia is a part of angular momentum, it necessarily includes all of the complications of moment of inertia, which is calculated by multiplying elementary bits of the mass by the squares of their distances from the center of rotation. Therefore, the total moment of inertia, and the angular momentum, is a complex function of the configuration of the matter about the center of rotation and the orientation of the rotation for the various bits. For a rigid body, for instance a wheel or an asteroid, the orientation of rotation is simply the position of the rotation axis versus the matter of the body. It may or may not pass through the center of mass, or it may lie completely outside of the body. For the same body, angular momentum may take a different value for every possible axis about which rotation may take place. It reaches a minimum when the axis passes through the center of mass. For a collection of objects revolving about a center, for instance all of the bodies of the solar system, the orientations may be somewhat organized, as is the solar system, with most of the body's axes lying close to the system's axis. Their orientations may also be completely random. In brief, the more mass and the farther it is from the center of rotation, the greater the moment of inertia, and therefore the greater the angular momentum for a given angular velocity. In many cases the moment of inertia, and hence the angular momentum, can be simplified by where is the radius of gyration, the distance from the axis at which the entire mass may be considered as concentrated. Similarly, for a point mass the moment of inertia is defined as where is the radius of the point mass from the center of rotation, and for any collection of particles is the sum. Angular momentum's dependence on position and shape is reflected in its units versus linear momentum. Kilogram square meter per second, nms or js for angular momentum versus kilogram meter per second or ns for linear momentum. Angular momentum's units can be interpreted as torque seconds, work seconds, or energy seconds. An object with angular momentum of ln ms can be reduced to zero rotation by an angular impulse of ln ms or equivalently, by torque or work of ln m for 1 second, or energy of Lj for 1 second. The plane perpendicular to the axis of angular momentum and passing through the center of mass is sometimes called the invariable plane, because the direction of the axis remains fixed if only the interactions of the bodies within the system, free from outside influences, are considered. One such plane is the invariable plane of the solar system. Angular momentum in torque. Newton's second law of motion can be expressed mathematically, or force equals mass times acceleration. The rotational equivalent is or torque equals moment of inertia times angular acceleration. Because angular acceleration is the time derivative of angular velocity, this is equivalent to rearranging into a form suitable for integration, and an integrating with respect to time. Therefore, a torque acting over time is equivalent to a change in angular momentum. The constant can be interpreted as the initial angular momentum of the body, before the torque began to act. In particular, if torque then angular momentum, that is, if no torque acts upon a body, then its angular momentum remains constant. Conversely, or angular momentum equals moment of inertia times angular velocity, and its time derivative is, because moment of inertia is constant, is zero, and which, as above, reduces to therefore, the time rate of change of angular momentum is equivalent to torque. If angular momentum is constant, and no torque is applied, conservation of angular momentum. Conservation follows mathematically from isotropy, or continuous directional symmetry of space, that is, no direction in space is any different from any other direction. See Noether's theorem. A rotational analog of Newton's third law of motion might be written. In a closed system, no torque can be exerted on any matter without the exertion on some other matter of an equal and opposite torque. Hence, angular momentum can be exchanged between objects in a closed system, but total angular momentum before and after an exchange remains constant. Similarly, a rotational analogy of Newton's second law of motion might be: a change in angular momentum is proportional to the applied torque and occurs about the same axis as that torque, since a torque applied over time is equivalent to a change in angular momentum. Then if torque is zero, angular momentum is constant. As above, a system with constant angular momentum is a closed system. Therefore, requiring the system to be closed is equivalent to requiring that no external influence, in the form of a torque, acts upon it. A rotational analog of Newton's first law of motion might be written: a body continues in a state of rest or of uniform rotation unless compelled by a torque to change its state, thus with no external influence to act upon it. The original angular momentum of the system is conserved. The conservation of angular momentum is used in analyzing central force motion. If the net force on some body is directed always towards some point, the center, then there is no torque on the body with respect to the center, as all of the force is directed along the radius vector, and none is perpendicular to the radius. Mathematically, torque because in this case in a parallel vectors. Therefore, the angular momentum of the body about the center is constant. This is the case with gravitational attraction in the orbits of planets and satellites, where the gravitational force is always directed toward the primary body, and orbiting bodies conserve angular momentum by exchanging distance and velocity as they move about the primary. Central force motion is also used in the analysis of the Bohr model of the atom. For a planet, angular momentum is distributed between the spin of the planet and its revolution in its orbit, and these are often exchanged by various mechanisms. The conservation of angular momentum in the Earth-Moon system results in the transfer of angular momentum from Earth to Moon. Due to tidal torque the Moon exerts on the Earth, this in turn results in the slowing down of the rotation rate of Earth, at about 65.7 nanoseconds per day, and in gradual increase of the radius of Moon's orbit, at about 3.82 centimeters per year. The conservation of angular momentum explains the angular acceleration of an ice skater as she brings her arms and legs close to the vertical axis of rotation. By bringing part of the mass of her body closer to the axis, she decreases her body's moment of inertia. Because angular momentum is the product of moment of inertia and angular velocity, if the angular momentum remains constant, then the angular velocity of the skater must increase. The same phenomenon results in extremely fast spin of compact stars when they are formed out of much larger and slower rotating stars. Decrease in the size of an object 10 times results in increase of its angular velocity by the factor of n2. Angular momentum in orbital mechanics, in astrodynamics and celestial mechanics. A massless angular momentum is defined called specific angular momentum. Note that mass is often unimportant in orbital mechanics calculations, because motion is defined by gravity. The primary body of the system is often so much larger than any bodies in motion about it that the smaller bodies have a negligible gravitational effect on it. It is, in effect, stationary. All bodies are apparently attracted by its gravity in the same way, regardless of mass, and therefore all move approximately the same way under the same conditions. Solid bodies for a continuous mass distribution with density function ρ, a differential volume element dv with position vector r within the mass has a mass element dm equals ρ dv. Therefore, the infinitesimal angular momentum of this element is, and integrating this differential over the volume of the entire mass gives its total angular momentum. Collection of particles center of mass. It is convenient to develop the equation of angular momentum for a collection of particles in motion about an arbitrary origin by resolving their motion into components about their own center of mass and about the origin. Given is the mass of particle, is the position vector of particle versus the origin, is the velocity of particle versus the origin, is the position vector of the center of mass versus the origin, is the velocity of the center of mass versus the origin, is the position vector of particle versus the center of mass, is the velocity of particle versus the center of mass. The total mass of the particles is simply their sum. The position vector of the center of mass is defined by inspection, and the total angular momentum of the collection of particles is the sum of the angular momentum of each particle, expanding. It can be shown that, and therefore the second and third terms vanish, the first term can be rearranged, and total angular momentum for the collection of particles is finally. The first term is the angular momentum of the center of mass relative to the origin. Similar to single particle, below, it is the angular momentum of one particle of mass m at the center of mass moving with velocity v. The second term is the angular momentum of the particles moving relative to the center of mass, similar to fixed center of mass. Below. The result is general. The motion of the particles is not restricted to rotation or revolution about the origin or center of mass. The particles need not be individual masses, but can be elements of a continuous distribution, such as a solid body. Rearranging equation by vector identities, multiplying both terms by 1, and grouping appropriately, gives the total angular momentum of the system of particles in terms of moment of inertia and angular velocity. Simplifications: single particle in the case of a single particle moving about the arbitrary origin, and equations and for total angular momentum reduced to fixed center of mass for the case of the center of mass fixed in space with respect to the origin, and equations and for total angular momentum reduced to angular momentum. In modern theoretical physics, angular momentum is described using a different formalism, instead of a classical pseudovector. In this formalism, angular momentum is the two-form no-ether charge associated with rotational invariance. As a result, angular momentum is not conserved for general curved spacetimes, unless it happens to be asymptotically rotationally invariant. In classical mechanics, the angular momentum of a particle can be reinterpreted as a plane element, in which the exterior product replaces the cross product times. This has the advantage of a clearer geometric interpretation as a plane element, defined from the x and p vectors, and the expression is true in any number of dimensions, in Cartesian coordinates, or more compactly in index notation. The angular velocity can also be defined as an antisymmetric second-order tensor, with components omega ij. The relation between the two antisymmetric tensors is given by the moment of inertia, which must now be a fourth-order tensor. Again, this equation in L and omega as tensors is true in any number of dimensions. This equation also appears in the geometric algebra formalism, in which L and omega are bivectors, and the moment of inertia is a mapping between them. In relativistic mechanics, the relativistic angular momentum of a particle is expressed as an antisymmetric tensor of second order. in the language of four vectors, namely the four-position x and the four-momentum p, and absorbs the above L together with the motion of the center of mass of the particle. In each of the above cases, for a system of particles, the total angular momentum is just the sum of the individual particle angular momenta, and the center of masses for the system.